Hello everyone, I hope you are doing well. So in today's video, we are pretty much going to go through the 2024 VCE sample physics paper that just came out recently. And so today, basically, we're going to go through the short answers and continue off through questions 9 to 15. And like always, guys, before I start this video, if you guys want private tutoring in specialist methods, physics, or chemistry, you can always email me through this email. Again, I just want to kind of restate this. This video is my suggested solutions to the exam. So basically, I believe that basically VCAR, when they, post a sample paper, they don't actually create solutions for them. So basically, these are going to be my suggested solutions. Again, if you guys see any mistakes, a slight mistake, please let me know and I'll check it. I hope this video finds you well and it helps you with your VCE studies. And yeah, let's smash through this video. Question 9. Dairy farms Joe and Phoenix are not connected to mains electricity. They use a diesel generator to generate electrical energy, concerned about their carbon dioxide emissions. They decide to install a 12 kilowatts bank of solar voltaic cells, solar panels in a paddock on their farm. Yes, so this is one of the new study design statements. So basically photovoltaics. So yeah, let's have a try at seeing how they basically write questions for it. They have 24 solar panels in their system, as shown in figure 10. These solar panels can deliver 12 kilowatts of electrical energy in full sunlight. Joe and Phoenix connect their bank of solar panels to an inverter attached to their dairy so that they can run the standard electrical equipment that would normally be powered by the mains power supply. A schematic diagram is shown in figure 11. Beautiful. Makes sense. Question A. Show that the output of each solar panel under full sunlight conditions is 500 watts. Easy. So we know that how much is the total power? So the total power was for the full 24 solar panels was 12 kilowatts basically. So 12 times 10 to the power 3 to get it in watts. So and if we have 24 solar panels, each will basically PE means like P of each, so the power of each. It's basically the total power divided by that 24, and this will give us the power consumed by each solar panel basically. Or basically the output, how much they produce power basically. So 24 solar panels. So that's gonna give me 12 10 to the power 3 24. That gives me 500 watts. And so, yeah, we have shown that. Beautiful. Joe and Phoenix have lost their instructions that detail how to connect the individual solar panels together. They measure the output current of one solar panel in full sunlight and give a steady 20 amps. Calculate the voltage output of one solar panel. Okay, so we basically know that for only one solar panel, they measure 20 amps of current, and we know the power that each solar panel produces, so we can easily calculate the output voltage for one solar panel. So that's going to be basically P equals IV. So we know the power is 500 watts. Your current is 20 times your voltage. So we get basically 25 volts. Beautiful. So using the following information to answer part C and D and E, Joe and Phoenix measure the resistance of the wire connecting the bank of solar cells to the dairy and find that the total resistance of those two wires is 1 ohm. And Joe suggests that the 24 panels should be placed in a series circuit as shown in figure 12, while Phoenix suggests that the 24 panels should be placed in a parallel circuit as shown in 12b. Alright, so we can see series and parallel. Beautiful. Alright, C. Calculate the total voltage and current output for the 24 solar panels if they are placed in a series circuit. Okay, what do we need? What do we know? So when they're placed in a series circuit, we know that these voltages, so the voltage of each solar panel basically adds up when it's in a series. Well, the current stays constant. We know that for a series circuit. So calculate the total voltage and the current output for the 24 panels if are placed in a series. So if you're basically placing them in a series, like we said, the current is going to be the same. So what's a current? You just need one current for one individual solar panel, and that'll give you basically the overall current when it's in series, so 20. So basically it's going to be 20 actually, because it's going to be the same. But the total voltage, the voltages are going to add up for each of the solar panels. So basically your voltage total is, because we have 24 solar panels, there's going to be how many? We know that each voltage is 25. Each produces 25 volts. Basically, we have 24 times 25. Basically, that gives me 600 volts. So that will be the output voltage and the current that will be produced by the solar panels if they place in a series circuit. I just want to basically draw a nice circuit to kind of help you these questions. So I want to just kind of represent. So here, ooh, why is this really? Okay, let's say we have circuit. So this is our photovoltaic cell. Basically, it looks like that. Where, of course, this is our series. So basically, this is your positive, this is negative. And so this is our solar panel, basically. This is a photovoltaic cell. And so basically, we're producing 600 volts when it's at series. But be careful, we also have a resistor because of the wire. We have resistance in the wire, of course. There's two. And I want to make sure the farm is basically like a light globe. I have to make it like a light globe, basically. So consider this as the farm, that light globe as a farm. All right. Perfect. So this is like a nice circuit to kind of simplify everything. So we have, again, so if we had one individual create 20 amps, the whole system has 20 amps of current. Beautiful. And the voltage basically adds up. Calculate the total voltage and current output for the 24 solar panels if they are placed in a parallel circuit. Now, this is just going to be the opposite. So basically what happens is that current adds up, whereas the voltage stays constant. Remember, when you have the solar panels in basically a parallel circuit, the voltage is basically, they both have each a voltage of 25 volts. So the overall voltage of the thing is going to be 25. So calculate the total voltage of the current output for the 24 cells if they place. So we know that the voltage is going to be the same, so 25 volts. And we know that the current is basically going to be added. So it's like the opposite compared to the series. So your current total is, we have 24 times, so we have 20 solar panels, and they basically each produce, I think, was 20 amps. Yep, 20 amps of it. Beautiful. 4 times 20. We basically get 480 amps. Beautiful. E. Determine who is correct regarding the type of circuit they should choose. Joe, who suggests a series circuit, or Phoenix, who suggests a parallel circuit. Now, absolutely, Joe is correct. You gotta realize straight away that having a series circuit, why is it actually advantage? It's very advantage, like in terms of why is it such an advantage? Well, let's have a look. Look at this series circuit. We're creating a high voltage. We're creating a very, very high voltage, but also our current is very low, which is very beneficial because what happens? Remember, this is 1 ohm. This resistance in the wire is 1 ohm. If you have, remember, the power loss in the wire, power loss is equal to I squared R. If you basically, like for example, the series circuit, why is it good? Because we have a very low current. So with this low current, what happens is we will have only little power loss in the wires, because remember, power loss in the wires is I squared, so your current gets squared. Whereas if it was your, using your parallel circuits, look at the current, 480 amps. If you had 480 amps, imagine squaring that. Guess what? The power loss will be so significant that there would be only little power given to the farm. So it's not very efficient. So having a series circuit is 10 times better than having the parallel in this case. And also, you create a high voltage, basically. You produce a high voltage also. It's also a great way. But overall, I think they're trying to look, basically, they're trying to look for students, understanding the power loss in those load or the wire. So you want to kind of maybe, to get full marks, you want to explain how, using low current is advantage because power loss is small and hence more power is delivered to the farm. Hence, using parallel circuit is a disadvantage as large power loss because of the current. That's it. You'll say something like that. Let's answer that question. So justify answer. All right. So first we're going to say who's correct. So we're going to say Joe is correct. Joe is correct. All right, so let's say, what we're going to say is basically using a series circuit, create a high voltage output, and with a low current output. Having low current is an advantage, as there is not a lot of power loss to the wires, and hence more power is delivered to the farm. Beautiful. And so now explain why Phoenix having a parallel circuit is very disadvantaged. So using a parallel circuit is a huge disadvantage. So disadvantage. So using it as there is a large power loss in the wire due to the high current. Beautiful. I think that goes basically in very deep detail. And yeah, it should give you those easy 3 marks. I think just specifying all these here. Beautiful. F. Explain the role of an inverter to ensure the correct operating of all standard electrical equipment in the dairy from the input provided by the 12 kilowatt bank of solar panels. It's very important. What is an inverter? So basically an inverter it's like a machine. What it does, it's like a thing that basically converts DC to AC. It's used because what happens is basically when you're using your solar panels, the actual electricity that is produced by this solar panel is actually DC, so direct current. And so it's quite useless in terms of using them for like your house appliances, because all your house appliances are basically made to be used by AC, so basically alternating current. So the way we can fix that is basically what we use is an inverter, and what an inverter does is it takes that direct current from the solar panels and it converts it to AC current. And so with this AC current, we can use it for our home, and so they can use it for their farm. So yeah, that's what it's only 1 mark basically. Let's write that. All right, so we say solar panels produce DC while standard electrical, so they were talking about electrical equipment, so electrical equipment runs on AC. An inverter is required to convert DC to AC, allowing solar power to be used in the farm. Beautiful. I'm running a lot, but I'm running a lot just to kind of give you guys, when you read them, you can straight out understand what I'm saying. So yeah, I'm trying to go in a lot of detail, but yeah, basically still answering the question. Yeah, that looks good. So solar panels, yep, produce DC or standard electrical equipment runs on AC, and inverter is required to convert DC to AC, so allowing solar power to be used in the farm. Beautiful. Question 10, let's have a try at this. Students are looking at young double slits interference pattern produced by a monochromatic light source, and note the central bright band and alternating dark and light bands on either side as shown in figure 13. The bright region marked C is in the center of the pattern, the dark region marked X is in the third dark band to the right of the center. Explain why the band marked X in the figure 13 is a dark band. Okay, so basically it looks like it's white. I know it looks like white because what I've done is basically, when I've took the exam, basically I make it black and white, and so that's why it's in this kind of template. Basically, this is black. In the real paper, when you have it white, and yeah, this is black. So it's actually a dark band. That's what they're saying. And we just basically need to explain, why is it a dark band? These are one of the most easiest questions. You need to state two things. You need to state its path difference, and then say it's destructive interference. These are the way you get full marks. So let's calculate its path difference, basically. Well, we know it's a dark band, so destructive interference happens. So we know that for destructive interference, so PD, your path difference is basically n minus half lambda. So our n is basically, because it's our third one, so n's 3 basically, half lambda. So basically it is overall 2.5 lambda. So basically that is our path difference. And you can see that it's not an integer value of the wavelength. So it's not constructive interference, it's straight away destructive interference. So basically this will get you the mark, one mark, and the other one basically say, hence destructive interference occurs at X, basically. Beautiful, so for 2 marks. B, the frequency of light source is increased. So your frequency, that's right, so F is increased, and the students note a change in the spacing. What would need to be done to the slit separation to return the pattern to its original spacing? Justify your answer. Okay, let's think about it. If you increase your frequency, you're basically decreasing your wavelength. And so what's going to happen to your spacing? We know spacing is change in X, which is basically wavelength over L over D. All right, so if you basically decrease your wavelength, you're decreasing your spacing. So basically what's happened is there's going to be a decrease in spacing. But what we want to do is, what should we do with D, our slit separation, to basically bring it back to the original? So if we want to bring it back to the original, what we want to basically want to do is, we want to, because our slit separate, our spacing decrease, we want to increase it. We want to do the opposite to make sure it goes back to the original. And so what can we do with D? What change should we do with D? We have to decrease your slit separation, because if you decrease your denominator, you increase your change in X. So overall, what we need to do is we need to decrease our separation, basically our slit separation, to do that. So let's basically write that down. So let me take this out. All right, so let's just say decrease slit separation. And so the number mark is basically just explaining it. So the spacing will decrease due to increase frequency. So yep, so basically to compensate, we want to increase spacing from change in X equals wavelength over L over D, decreasing the slit separation. So decreasing the slit separation will increase the spacing. That is it. I mean, that goes into, yep, explaining it in very detailed. Yeah, that looks perfect. C, explain how the results of this experiment could support a wave model of light. What a beautiful question to end the question. Basically, this question comes up in many of the exams. It's so easy to get full marks. What you basically need to how do these results basically prove or support the wave model? This is what we say. You first see that, we can see that there's constructive and destructive interference happening, and because of the dark bands and basically the white bands, or the bright bands. What this is proving is that interference is happening. This tells us that there's an interference pattern. And if you remember, interference is a wave phenomena. And so if it's a wave phenomena, it supports the wave model. That's all you need to say. It's very easy to get full marks with this. So let's write that down basically. So the experiment proves interference from constructive and destructive interference. So interference patterns, basically. This is a wave phenomena. This is a wave. Basically, this is wave phenomena. That's a struggle to spell that. And hence, supports the wave model. The wave model. Beautiful. Done. Beautiful. Question 11. Bruce and Denise are discussing the effect of light frequency on photocurrent in the photoelectrical cell while investigating the photoelectrical effect. Straight away, just hearing light, how does, basically they're discussing the effect of light frequency on photocurrent. Now, you should already know that frequency is independent on photocurrent. It doesn't affect photocurrent. Remember, frequency will only affect the stopping voltage and photocurrent will only get affected by the intensity of light. Beautiful. Figure 14 shows a graph of the photocurrent against the voltage applied across the photocell. Using a monochromatic light source of wavelength this, they record the maximum photocurrent to be this and a stopping voltage of that. Determine the work function of the metal in the photocell Bruce and Denise are using. So we want to determine the work function. Now, because we're given the stopping voltage and we're also given the actual wavelength, we know that the stopping voltage, so your stopping voltage, is basically equal to your kinetic energy max, basically, EK max, basically. And so we know our EK max formula. Our EK max formula is basically your HF minus your, so you minus your work function. Now, HF is basically just energy. And so because we have it in terms of, we don't have frequency, it's in terms of wavelength, well, we can just replace that with hc over wavelength. So still gives us energy, basically. So this is a formula that we're going to basically use to calculate that, which basically means that to calculate your work function, it's hc wavelength minus your EK max, which is our stopping voltage. So this is our formula. So let's write everything down. So your H is having a look at my formula, it's 4.14 times 10 to the negative 15. Times your C value, so 3.0 times 10 to the power of 8. That looks alright, so times 10 to the power of 8, all being divided by your wavelength, which is 450, times 10 to the negative 9, and you're going to minus your stopping voltage, which is 0.47. Alright, so that should give me my value. So 4.14 times 10 to the negative 15, 3.0 times 10 to the power 8, 450 times 10 to the negative 9, minus 0.47. And so basically gives me 2.29 electrovolts. That's my work function. Beautiful. Next question. The monochromatic light source is now changed to the one with a wavelength of 400 nanometers. So wait, is there a decrease? Yeah, they decreased. It was 450 nanometers. Now they've basically made it to 400. So they've decreased your wavelength. And so and it delivers the same light output as the original source. So if it delivers the same output power, what it tells us is that the intensity is not changed. Intensity is the same. So basically the photocurrent is going to be still. It's not going to get affected. Bruce predicts that the stopping voltage will become 0.82. Now he's correct, because if your wavelength is gone down, it means your frequency has gone up. And if your frequency goes up, it means your stopping voltage has gone up. So yes, it's good that he said the stopping voltage will go up and the maximum photocurrent will decrease. Rubbish. Not true. Remember, photocurrent, he hasn't touched the intensity. The intensity is the same. So the photocurrent is not going to decrease. It's going to stay the same. So he's basically got that part wrong. So I'm going to highlight that like that. Dennis agrees with the stopping voltage production, but states that changing the wavelength only affects the stopping voltage. Good job, as the photocurrent is dependent on the intensity. Yes, Denise is correct in this case. Absolutely, Denise has, whatever we said, Denise has basically corrected us. So yeah, so she's correct. So she said that the stopping voltage changes because of the wavelength, but the photocurrent is dependent on the intensity, which is great. So evaluate Bruce's and Denise's argument. It's not telling me which one's right, So we just basically need to evaluate them. So let's do that. All right. Okay. So first we're going to say is whatever we said. So we're going to say decreasing. So I'm going to write a lot. I'm going to go in detail basically to answer this question to help you guys out. So decreasing the wavelength increases frequency, of course. So increases frequency, which increases the stopping voltage. Yep. Hence, Bruce is correct. Hence, Bruce is correct. So hence Bruce is correct. Understanding of the photoelectric electric effect. So that's what I said. He's correct. However, different color, so I can show that nicely. However, Bruce incorrectly predicts that the maximum photocurrent, so the maximum will decrease. The maximum photocurrent is independent. So it's independent on frequency. That's what we know. And is dependent on the intensity, basically, which is constant. We know it's constant because the light output remained constant. So constant as the light output remained constant. Beautiful. And now we need to basically explain Denise now. So Denise is correct. So we just need to say, let's say, so. All right, so Denise is correct in stating that changing the wavelength, which remember, it affects the frequency. So I'm going to write frequency like that. So changing the wavelength only affects the stopping voltage. Not the maximum photocurrent, as this is supported in the photoelectrical effect. In the photoelectric effect. Beautiful. And that, of course, this is not what you want to do in the VCA exam. You don't want to write this much. But what I want to do is basically, kind of written a lot just to kind of give you more, to give you a little bit more easier understanding. So when you read it, you can easily understand what I'm basically pulling out from the information. Yeah, this looks very good. I'll try to be so much detailed with my answers. And yeah, I hope that kind of helps you, understand how to get this answer. Question 12, let's smash through this one. All right, let's use a different color, this one. Students are comparing the diffraction pattern produced by electrons and X-rays in which the same spacing of bands is observed as shown in figure 15. Note that both the patterns are shown are the same scale and use the same sample. So we have electrons and X-rays. We can see that they basically have the same diffraction pattern. Explain why electrons can produce the same spacing bands as X-rays in a diffraction pattern. This is an easy question. It comes up in the exam so many times. But it depends on the marks. because it's 3 marks, you just a little bit need to be more kind of detailed in your questioning. So if because of 3 marks, you want to basically state 3 things. I think just easily 3 things. You just want to say that diffraction is like dependent on the wavelength. From the formula, remember that diffraction is dependent on the wavelength over width. So we know that diffraction is dependent on the wavelength. And because electrons actually have a de Broglie wavelength, so electrons, remember, they can behave as waves. So they do have a de Broglie wavelength. Electrons and X-rays at the end of the day must have the same wavelength to produce the same pattern, the same spacing, diffraction pattern, basically. And that's all you need to basically say. It's very nice and easy, this one. So let's rip that out. There's a color blue, basically. So just 3 dot points that are very nice. I've done this question so many times in exams. It's very easy to get full marks. So diffraction is dependent on wavelength from, we said that D is proportional to wavelength over width. So that's our formula. So electrons have a de Broglie wavelength. We actually give a formula with that, so because we know that wavelength is equal to h over square root of 2 mke, your kinetic energy. So that's the formula for a de Broglie wavelength. And so what does that basically tell us? That electrons and X-rays must have the same wavelength to produce the same pattern. The same, basically, pattern. Beautiful. And that goes in detail, yeah. Next question, B. So the electron diffraction pattern is produced by electrons with energies of this. Calculate the wavelength of these electrons. Let's do that. So we know that, okay, that's our energy. We want to make sure to change it in like joules. So that's our kinetic energy. So your kinetic energy is at 3.0 times 10 to the power 3. Make sure you times it by, make it like, joules, which is just times it by 1.6 times 10 to the negative 19, which gives me times 1.6 times 10 to the negative 19. So that basically gives me 4.8 times 10 to the power of negative 16 joules. Now, we have in joules, we know that we can easily calculate the momentum. So momentum is basically the square root of, so it's square root of 2m kinetic energy. So let's write that down. So it's basically 2 times the mass of an electron, which is negative 31, times your kinetic energy, which we got, which is 4.8 times 10 to the negative 16. And so that gives me square root 2 number 1 times 10 to the negative 31. And so there I get a momentum of basically 2.95 times 10 to the negative 23 kilograms meters per second. That's my momentum. And so we know that wavelength is h over momentum. So let's do that. So h is basically 6.6. Let me have a look at it. It's in my summary sheet. 6.63 if I'm not mistaken. 6.63 times 10 to the negative 34. All divided by this momentum. Beautiful. So that gives me your wavelength actually is basically 2.24 times 10 to the power of negative 11. Beautiful. That is right. That looks good. All right, question 13. Let's have a try at this. Up in the late 80,000s, it was thought that light waves, like other waves, needed a medium to travel through. Scientists at that time theorized that space was filled with a medium called the ether, and that electromagnetic waves travel through this ether. In the late 18,000s, Michelson and Morley provided an experiment to try to provide evidence for this existence of the ether. Michelson and Morley hypothesized that as Earth moved around the sun, it travels through an ether. Hence, there should be a difference in the measured speed of light depending on whether the light is traveling parallel or perpendicular to the direction of the Earth's movement through the ether. Identify what Michelson and Morley's experiment actually showed and explain how this result supports Einstein's special theory of relativity. This here is actually brand new to the study design. So it's not brand new actually. It used to be in the old study design. So if you guys want more practice in like the Michelson and Morley questions, I think the old questions, like I believe, like if you look at the 2003 questions to like 2007, there should be a lot of these kind of questions in the special relativity section of it. So these are great practice. So you can get a lot of practice in this kind of questions, especially the Michelson. This is brand new to this new study design right now. So yeah, let's actually now answer this question. So what it's saying is identify what Michelson and Morley's experiment actually showed. So what it was basically is that Michelson and Morley basically they experimented and they were like, hey, let's actually prove that the medium that the light basically goes is the ether, and so let's actually prove that there is an ether. And so what they did was, the way they actually did that is they tried to basically put an apparatus that basically was used to basically measure the change in speed of light by basically observing its behavior relative to the Earth's motion through the ether. So because the Earth moves, they basically they knew that the ether would change the speed of light because it's coming through a medium. And if they got that change, if they saw a change in speed of light, this would prove that there is an ether, basically, that Earth is going around with. So that's what they wanted to prove. And so they did that by basically, they took light and they basically hit it into and split it basically into two paths, which one was of course parallel like they said, and one was perpendicular to the Earth's motion. But basically when these two lights basically came and recombined, what happened is that there should be an interference pattern that would be produced. And so this interference pattern would basically show the differences in light speeds along those paths. And so of course they hypothesized that there's going to be a change in the speed of light, which proves that there's an ether. But surprisingly, they found that there was no evidence of the changing of this light of speed, and they're like, why is that? Wait, if there is no change in light speeds, that's going to be a problem. Even regardless of changing the Earth's motion, like even though sometimes of course the Earth moves, orbits around the sun, so they were like, look, we'll do this experiment, we'll repeat it as many times as we can, like they did in 6 months, and it still gave the same results. It always was the same speed of light. So basically this result basically contradicted the whole kind of thing about the existence of the ether. But it also kind of it actually also indicated that the speed of light is actually a constant value, regardless of the Earth's motion, basically, as we stated. And so, yeah, they basically proved that the ether didn't even exist, but they also proved that the speed of light is actually always constant, even regardless where the Earth basically is, the Earth's motion. And so it says how this result supports Einstein's special relativity easily. Basically, Einstein's theory of special relativity, which is basically precisely the second postulate, which states basically the speed of light is constant regardless of the observer's motion, is basically supported by this experiment finding. Like we said, they proved that the speed of light remains constant, and his postulate states that the speed of light is constant regardless of the observer's motion. And yes, he basically proved it, and he basically supported Einstein's theory of relativity. So I think that's what you should write for these 4 marks. Yeah, that's a lot of marks. So I think I'm going to try to be very detailed in whatever I said, I'm going to basically write it, and hopefully I can detail and write as much as I can to help make you guys understand what this is. Especially this is new in the study design. But it's not a bad question actually. So we're going to say it's 1 dot point. So we're going to say the Michelson and Morley's experiment aimed basically to measure a change. So measure a change in the speed of light by observing its behavior relative to the Earth's motion. So Earth's movement, so Earth's motion through the ether, basically through the ether. And so let's do another color. So that should give you the 1 dot point basically. The other one is they split. Now we said they explained how it works. So they split a beam of light, we said, into 2 paths, which one was parallel and one perpendicular. So one perpendicular to the Earth's motion. So after basically recombining of these lights, so we said, so basically when those beams basically come together, recombine. So after recombining the beams, and interference, so what am I, oh my god, what am I doing? So an interference pattern, so an interference pattern would indicate basically differences in light speed along the path. Beautiful. And so another one is surprisingly, I'm going to say surprisingly, Michelson and Morley found no evidence of changing light speeds. So light speed, regardless of the direction of the Earth's motion, Earth's motion through space. So through space, basically this result, so we say this result contradicted the expectation. So the expectation based on the existence of the ether. Yep, indicating that the speed of light remained constant regardless of the Earth's motion, Wow, it's a lot of writing. And so basically how does this do? So basically we're going to say this Einstein's special relativity. So Einstein, who did not spell it, so Einstein's theory of special relativity. So special relativity, particularly the second postulate, so second postulate stating that the speed of light is constant regardless of the observer's motion. So observer's motion was supported by the experiment findings. So supported by the experiments finding. Now that's a lot of writing, to be honest. That's not what you want to do in exam. But yeah, I hope that kind of really details what the whole kind of answer is. Like, of course, you want to basically, those, if you see all, those highlighted person, these are the dot points. What you basically want to do is summarize them in such little parts. Be specific with the answer, but I basically, just to help you understanding, I want to be very detailed in my answers so you can guys understand what the question basically telling you. And yeah, to understand what the question is. Beautiful. Question 14, let's have a try at this. The visible spectra of hydrogen absorption and hydrogen emissions under certain conditions are shown. Beautiful. So we have the hydrogen absorption spectrum and the hydrogen emission spectrum. Explain how the hydrogen absorption spectrum is produced. Beautiful. An easy question. Well, so basically what a hydrogen absorption spectrum is, how it's produced is this. What you have is basically you have a hydrogen atom. So you have an hydrogen atom. So you have a hydrogen atom, and basically you take like a spectra which you basically take a continuous spectrum. What am I saying? So basically what you do is you basically shine a full spectrum of light into the atom. And so basically what's going to happen is that some of the electrons are going to absorb certain frequencies or wavelengths of that photons or the light. And so what the electrons are going to do is they're going to basically transition from low energy states to higher energy states. And so only certain, as you see, normally it's rainbow, but here's a little bit. So normally this whole thing is rainbow. So if I show you, this would be like a rainbow. The white parts would be rainbow. And you can see that there's dark bands, basically. And those dark bands are those certain frequencies that basically the hydrogen atom, that electrons basically absorb, which are the certain wavelengths that they actually absorb for it to go from low energy state to a higher energy state. And so, yeah, I hope that makes sense. That's how they're basically produced. And yeah, and that's why there's basically dark bands. Let's write that. I mean, it's very easy to kind of get full marks for this. Basically, just describing how it's created. So let's kind of be detailed with this. So what we can say, explain how the hydrogen, so an emission spectrum. So basically, we say not emission. What am I saying? It's absorption, isn't it? Yeah, absorption. And the other one's, what am I looking at that one? So an absorption we're talking about. So basically the absorption spectrum, the absorption spectrum shows the wavelengths. You can see those wavelengths, those certain wavelengths basically. Shows the wavelengths of light that hydrogen will absorb. So absorb when the full spectrum of light is shown through it. Yep, so that makes sense. And then specific wavelengths are absorbed by the electrons, resulting in dark bands. Basically they correspond, so corresponding electrons going from, so electrons transitioning from low to high energy state. So from low to high energy state. Beautiful. And yeah, and then explain how the hydrogen emission spectrum is produced. So it's the same question, but basically in the opposite way. So how is basically the emission spectrum is basically it's like the same thing, but the opposite. So what it is, you take a hydrogen atom, and basically when the hydrogen electrons are very excited, so they have a lot of energy. What they're going to do is basically go from high energy states to low energy states. And when that happens, when they transition down, what's going to happen is they release photons. And so these photons, it's energy. And so they release basically certain wavelengths. And what the emission spectrum does is it measures those. It measures those, those certain frequencies that it emits, basically. And yeah. And so don't forget also that the emission spectrum is it's the same as the continuous spectrum. So the emission spectrum is the same as the absorption spectrum, as you can see, but the only difference is that the thing here is darkened. Basically, the thing here is darkened, where you would see only these white parts are going to be where the rainbows. It's going to look like a rainbow, by the way, where those certain frequencies are basically emitted. So if you look at it here, if you basically put these together, it will be a full rainbow, basically. It will be the full a continuous wavelength, the continuous light, the continuous spectrum of light. But because, they basically you can see that some are absorbed. So what's going to happen is you can see some gaps are being absorbed. These are the ones that are being absorbed. And here are they. And basically, it's the same. When they emit, it's basically when they basically transition. And so it's here. Does that make sense? Yeah. Beautiful. So basically what we're going to say here. All right. So we're going to say an emission spectrum, basically. Spectrum consists, or actually not consists, shows frequency, so it shows the wavelengths of light that a hydrogen atom, will emit when the electrons are excited. That's it. And basically one more mark, basically just, so it consists of the same continuous spectrum. So continuous spectrum that has been darkened. But with bright bands, basically. The difference, but with bright bands at the wavelength of light that the hydrogen emits. Beautiful. Oh no, not the hydrogen, the electron, we want to say. The electron emits. That the electrons emit. Beautiful. That looks nice. Perfect. The question for this is the last one. I think it is. What a long question. Yes, it is. It's the last question. Very, very long. Let's smash this one here. All right. Question 15. Let's have a try at this. So two physics students, Ishva and Magnus, are investigating circular motion and centripetal force. Figure 17 shows the experimental setup and the apparatus that the student uses. Beautiful. So it's actually the same apparatus that was used in the 2021 VCA exam. Yep, so we have a mass rubber stopper, strong cord, position marker, metal washers, and slotted glass tube. Yep. In reality, the students find that the cord is not quite horizontal but dips downwards slightly due to the gravitational force acting on the rubber stopper. The physics teacher assures them that this will not invalidate their investigation. Ishva holds the glass tube and sets the rubber stopper rotating at a horizontal circle of radius 0.75. So she maintains a constant radius of the circle by keeping the position marker at a fixed position just below the bottom of the glass tube. Alright, so just bottom of the glass tube. So Magnus uses a stopwatch to measure the time for 20 revolutions of the rubber stopper. The experiment is then repeated 5 more times with the extra metal washers being added before each new trial is undertaken. Each washer has a stated mass of 30 grams with an uncertainty of 0.1 grams. So what information about the uncertainty in the measurement value of the washer's mass is conveyed by this addition of 0.1. So the plus or negative of that 0.1. So what does that plus or negative 1? But this basically tells us that the actual mass could be basically 0.1 higher or heavier. Actually, no, higher means, yeah, it could be higher or lighter than reported, basically. So it's like the range, basically. So for uncertainty, that's plus or negative, it's just a range of units where it's in either direction from the stated value. So you can have it basically being heavier, or you can basically have it, so you can have it basically 0.1 heavier or 0.1 basically lighter. And so these are where your true value basically exists. So that's what our uncertainty basically conveys, those plus or negative 0.1. Let's write that down. Okay. Basically conveys uncertainty within a range of 0.1 units in either direction from the stated value, basically. Stated value. So basically suggests, I'm going to go in a little bit more detail to kind of help students that don't understand. So it suggesting the actual mass. So actual mass could be 0.1 units heavier or lighter, basically, or lighter than stated. Beautiful. Question B. The tension in the cord supplies the centripetal force that the rubber stopper needs to rotate in a circle. True. What is the cause of the tension? Beautiful. So we have a tension in this rope, basically. We have tension here. Let me draw in red. We basically have tension here. This is a tension force here. The thing that creates this tension is, remember, if you haven't done this experiment, basically when you rotate it, this wants to basically get out. It basically just, the mass wants to kind of fly out. And it doesn't, because what happens is when you put metal washers, the force of gravity of these metal washers basically cancels out with this tension force that the rope. And it's basically that metal washers, basically it's the thing that actually creates that tension, actually. So if you have a metal washers, it creates that tension. Beautiful. So if you haven't done it, if you put metal washers and basically rotate, yeah, and you put, like, the more heavy you do, the more tension the rope basically feels. So yeah, so the thing that creates those is basically the mass of the force of gravity of the metal washers. So the force of gravity of the metal washers. Beautiful. Magnus and Ishvar record their results in a table by accidentally leave 2 blank spaces as shown below. Fill in the blank spaces in the table below using 9.1 kilograms for your calculation. Okay, so we got the total mass of the washers, gravitational force acting on the washers, average. So we want period. Now, easy. Because we have the average time for 20 rotation, it's basically this divided by 20 to get the period. Because remember, the period is how long does it take for 1 rotation, not 20 rotation. So you want to basically divide it by 20. So 12.8 divided by 20 basically gives me 0.64. You can basically check this. If you do 14 divided by 20, you should get 0.7. Also, we got our period now. Let me double check that. So 14 divided by 20. Yes, so 0.7. That also, yeah, that works perfectly. Yep. And so we've got also left a gap here, which is basically frequency getting squared. So we know that frequency is 1.75. So what's 1.75? Basically squared. That gives me 3.06 basically. Is that right? I'm just going to try to check with this one. So if I square this, it should give me that. So let's say 1.56 squared. Yep, looks perfect. Done. All right. Next question, D. Ishva and Magnus fill in the blank spaces in their table and then plot the gravitational force acting on the washers, mg on the y-axis of the frequency, squared on the axis below. They then draw the straight line of best fit through the plotted points as shown in figure 18. Okay. So we've got that. Okay, we can straight away see this is an outlier. It doesn't actually lie on that graph. But yeah, it looks perfect. Alright, show that the relationship between the variable f, m, and the constants g, pi, r, the radius of the circle, and m, the mass of the rubber, for an ideally performed investigation of this kind can be expressed as this. Show all steps of your reasoning. Easy. So, we basically want to prove this formula. Alright, now from what we said that the force of gravity of the metal washer should be equal to your tension force, or remember that tension force is your centripetal force, basically, of your circle. So, what we want is the tension force. Oops, what's happening here? So your tension force must be equal, So your force of gravity of the metal washers is going to be equal to your centripetal force of the, I'm going to write tension basically, make it easier. The tension is your centripetal force basically. It's going to be the tension in that metal wash. So yeah, the rubber, what was it called again? Washers, the rubber stopper basically. So I know Fg is basically mg, but tension, remember tension is, so your tension is your centripetal force. We know that centripetal force, so looking at my formula sheet, what's the formula for centripetal force? So centripetal force is basically F net is equal to mv squared over r. Yep, so we have mv squared over r. Now, what do we need to actually know already? We know that velocity, we can replace velocity because velocity is not in here. We can replace that velocity. We know that velocity is also 2 pi rt, your period. So imagine that being squared. Basically, everything here is going to be basically squared. So it'll be 4 pi squared r squared over t squared. And we're basically dividing it by, you're basically multiplying m, and then you're dividing it by another r basically, so r here. And that's what's that going to give you basically? It's going to cancel these ones out, so you're basically left with your force net. Let me write that down. So your force net, that's your basically, yeah, this is your force net. So that's how we basically proved this. So 4 pi squared r, I'm going to use r, m, t squared basically. Now, of course, t squared, we want frequency. Now, we know that 1 over t is your frequency. But if we square it, which is 1 over t squared, you get frequency squared. So you can basically rub that part out and replace it with frequency squared. So we basically proved that formula. That looks good. Show all the steps. Yep, that looks good. That looks so ugly. Why is it like that? Yep, that makes sense. Beautiful. Alright, let's have a try at this one. 4 marks. So on the figure 18, extend the straight line of the best fit the students have plotted until it intersects the x-axis. Comment on the implication of this intersection point with respect to the student's investigation and the relationship in part DI, so the formula basically. So first, okay, let's extend it. What I'm going to do, just if I had a rule, let's say like this. So if I extend it, it's nicely like this perfectly. So where is it basically passing? So the x-intercept, which is here. It looks so halfway is here, which is 0.25. It's like around, we'll say it's estimate like 0.2. So that's your frequency scared. So basically, what is this telling me basically? This is telling me that my force of gravity, your mg of the metal washers, is actually 0 when your frequency squared is 0.2. Now, how the hell does that make sense actually? Because you got to think about this. Okay, what it basically means is that, looking at this formula too, let's have a look at this formula. It just means that this here is 0. Basically, your mg is actually 0, and basically you have a frequency. You actually have, some frequency. That doesn't make sense, because what it means is basically your force of gravity it basically means that, so remember G is a constant, so it basically says when your mass is 0, it means imagine not having a mass, so you actually don't even need a metal washer. You can actually basically produce a tension force or your centripetal force because you still have an existing frequency, as you say from here, which was, when did it drop out? It's 0.2 we said, which was 0.2. How does that make, that's rubbish. Because this contradicts everything that we were talking about. Remember what we said, that your force of gravity of the metal force is what basically creates that tension force. It's what creates that tension force, which is our centripetal force. And that's what basically keeps the rubber stopper moving in a circular path. How can, if you don't have those metal washers, you basically don't have a tension force, or basically your centripetal force, and hence you should have a frequency of 0. So this is a big contradiction, and we can actually prove it by the formula. So if your mg is 0, yeah, think about it like this. If your mg is 0, these all the constants from 4 pi squared, r, m, so these here are constant, they're just numbers. So how can we get basically this to be 0? You have to make the frequency squared be equal to 0. That's the only possible way. So your frequency squared had to be 0. And so why is it not 0? This means that there's basically a systematic error, highly a systematic error, because you can see that these values are nicely uniform. You can see how they're nicely uniform and the way they create a straight line. So basically, yeah, they probably had a systematic error in the experiment. But yeah, I hope that makes kind of sense. That absolutely doesn't make, I don't know how they got that. So basically it's supposed to pass through the origin. So if you have mg equals 0, this has to, your frequency squared has to be 0. I'm going to try to, because it's 4 mark, I'm going to try to be detailed as much, just to kind of help you out, to understand what I basically said, because it is kind of confusing. So I'm going to try to detail this. So basically what the intersection point tells us is, so the intersection point tells us that when the force of gravity of the washers is 0, there is a non-zero, basically not 0. It's supposed to be 0, but non-zero. We don't want to say 0.2 because that's kind of like estimating, and maybe that's not what they want to say. Non-zero. I'm still going to write it. So non-zero frequency produced. This means that there is no need for metal washers, producing a force of gravity, as the rubber stopper will still have a centripetal force due to the non-zero frequency, That's what it means. Now, this is so we're going to say this is, we have to say this is a contradiction. So basically use a different color now. So this is a contradiction, as the force of gravity is what causes, it's what basically causes the tension. And hence centripetal force that keeps the rubber stopper moving in a circular path. Beautiful. So that's basically just explaining, but of course we have to explain more because we need to state the relationship. How does it relate to the relationship of our formula? And hence, yeah, also that's what we need to do, and let's do that. I mean, there isn't a lot of space, so because I wrote too much, what I'm going to basically do is I'm going to write more by just using a different color. I'm going to write it at the bottom, basically. I'm just going to continue it at the bottom. So I'm going to continue it here. I'm going to then make them all smaller. So basically then, having... Alright, let's see what I can do here. What I can actually do, I'm going to write it down here, basically. I'm going to write it down here. And then I'm going to put it up there, basically, with it. So I'm going to just continue off here. So we said, okay, basically, now we need to use it, kind of show it. So we know that basically having 0 force of gravity should not produce any tension, and hence frequency should be zero. Beautiful. This is also supported by the formula. Basically, the formula also supports it as having, mg equals 0. So that mg equals 0, the other ones are constant, yeah. So as having mg equals 0, the only way we can, have that is if frequency is 0, as the frequency, let me write here, is the only, it's the only thing that we can basically change, that we can change while the others are constant, while the other values are constant. All right, and so I think just an extra, why is this? Probably this is just, like we said, a systematic error, basically. This is due to systematic error. This is due to systematic error, as the points basically are uniform. They're consistent, basically. They are uniform. And create a straight line. Oh my god, I've written so much. I don't even read. This is a lot, I know. Now, don't get stressed. You don't have to write this much. But what I've done is I've tried to go in detail explaining how I basically, let me put it like that. So this part here goes like there, basically. So basically that's the total thing, and I'm just going to make it shorter, basically. Make it more little. So now, there it is. That's very detailed in terms of those 4 marks, and yeah. Have we done it? Yep. So implications, with respect to students' identification, and the relationship. Beautiful. So calculate the gradient of the line of best fit plotted in the figure 18. Let's do that. This is one of my favorite. So we've already got that point. So we just need to take 2 points to get that gradient. All right, let's see which 2 points look nice. This point looks nice here. So it's like halfway. And it's 8. Also, we could pick this point that nicely lies on the graph itself. So here. So basically your gradient, your m, which is your gradient, is equal to your y2, your change in y, so which is 8 minus 4, which is basically 4. So which is basically, so it was 8 minus 4, all being divided by 2.75 minus 1.5. So 2.75. So 2.75 minus 1.5. And so that gives me what? What's basically 4 divided by 2.75 minus 1.5. Basically, 3.2. That looks quite great, 3.2. And so the gradient, I mean, the units for gradients, I mean, we can have a unit for gradient, but I think that's quite useless. The unit for gradients basically for this one's newtons, basically, newtons per divided by frequency squared, which is just basically hertz to the -2, basically. That's the unit for this. I don't think you need that. Newton hertz -2. Beautiful. Next question. Using the gradient calculated in part DII, determine the mass of the rubber stopper. Beautiful. So we know that the your gradient is what? It was your mg divided by your frequency squared. Now remember that formula. Let's come back to that formula where it was. It was mg equal, where is it? Oh my god, did I go down? Okay, yeah. Mg equals 4 pi squared. So basically it's mg equals 4 pi squared r mf, I think mf squared. Is that alright? Alright, that looks perfect. So if I divide both sides by f squared here, I cancel out this f squared, and guess what we get? We get the same statement here. So our gradient is basically, so our gradient, we can equate these two basically. So this is our formula, meaning that our gradient, which is basically that 3.2 is equal to 4 pi squared, your radius. We were given the radius, I think, in the beginning. Yep, 0.75. So 0.75 times your mass of the stopper, which is what we're trying to find. So m. So hence your m is basically 3.2 all being divided by 4 pi squared, 0.75. 4 pi squared times 0.75. And so that gives you basically 0.11 kilogram. Beautiful. And that looks nice. Last question? Yes. Wow. I'm just so tired. I'm not gonna lie. This is such a pain. We're nearly done at least. So, the graph in figure 18 shows one data point, 785,308. Where's that? 785? What? The x-intercepts go to max 4. Why do you mean so? I think they've made a mistake in terms of coordinates. I think they're supposed to switch these around, basically. They're supposed to switch them around. So that clearly does not fit for the line of best fit drawn by Ishva and Magnus. They discussed the possible reactions. So the one that doesn't fit is this one here. Let me rub these all out, basically. I don't want to kind of confuse a lot of students with this. Okay. So this is an outlier. That outlier that actually doesn't fit any. Basically, yeah. Basically mixed out the x and y's. So, yep, that's that point, basically. Yep. Beautiful. That's that point. What are they saying? They discussed the possible reasons for this. Ishva suggests that the number of washers might have been incorrectly counted, and Magnus suggests that the frequency might not have been incorrectly measured. Given the experimental method used, which unit is more likely to be correct? Now, Magnus is correct, of course. You should realize that, okay, Ishva is wrong, because the number of washers is, even if you messed up the masses, let's say, you messed up the number of washers and you messed up those masses, you remember that they basically, the total masses of all those washers are basically added to each other. So basically, if one was if you made one of a mistake, if you make you got that one wrong, what would have been is basically it would have still been linear, because you remember you're adding those masses, basically you're adding them all. You're adding them, even if you make one mistake, you're still adding it with the other one, so you still extrapolate basically, and so it should still be a consistent straight line. So yeah, having that, whereas the frequency, yes, you can actually have also frequency can really basically have that big effect on it. But yeah, having the washers, the mass, so the number of washers really doesn't explain why these are all straight lines. Basically, this is a straight line, but this is straight away outside of it. So no, that doesn't explain that. So there has to be the frequency, basically. I hope that makes sense. Yep. And so it is an outlier, yeah. And so, I mean, yeah, that's basically it. So I think just basically the first mark, I'm going to be very detailed in this, just 2 marks to explain how it works, how I got that answer. So let's use this, okay. So who was it right? Magnus, we said, yeah? Magnus is correct. Any error in counting the number of washes would likely, so basically we said would likely, I want to just double check before doing that, would likely. So even let's think about it looking at the graph. So you can see that the frequency, so having a look at this, you can see how they're kind of uniform. You can see that mg is actually uniform. Look at this. You've got this point here, mg, that point there, that point there, that point there. Can you see how it's still uniform? That point there and that point there. Now have a look at when it's frequency. You mess around with your frequency. That one's there. It still doesn't. Nah, that's not a good way to kind of look at it. Basically looking at symmetry, but no. That the best way is this way, basically. An error in counting the number of washes would basically likely lead to a consistent trend in the total mass. So total mass across all trials, basically across all trials. However, the data point, basically that, so that data point that. So, however, the data point is an outlier. Significantly different from the trend, basically. From the trend. This basically consistency. This inconsistency. What am I saying? This inconsistency. I think it's 10C. Suggests that the error. That the error is not related. To the number of washes. Basically, but the frequency. So it has to be the frequency. Beautiful. And that is it. I hope that makes sense. I hope you learned something through this video. I hope this video finds you well and helps you with answering most of the questions that, especially, it's a new study design, so your exam's basically going to look like this, approximately the same. So hope this, try to do in this paper. It's very good for you, so you can get a lot of practice, especially in how you would expect your exam to be. I hope this, video basically helped you. Please make sure to like and subscribe, and please tell your friends about this channel. I'm trying to basically grow this channel up. I hope you have a great day, and please make sure you take care of yourselves. Bye bye.